Okay. Okay. Thank you very much. Thank you very much also to the organizers for giving me an opportunity to speak. So I move from a different session. So I will slightly move to the more conventional superconductor in the sense that which are more in the regime of weak coupling. So there is gamma smaller than 1. But I would like to talk about the situation. So what I'm a bit confused why I have so many. Okay. Maybe I should change to the presenter mode. You think so? Okay, good. Okay, so what I'm going to talk is essentially how you can utilize the nonlinear response to probe excitation in a superconductor and essentially learn something about the nematicity. So the work that I'm going to present is summarized in these publications. And also let me acknowledge, since usually we don't have time to acknowledge the collaborators at the end, so let me just mention that the work I'm going to present has been done in collaboration with my students, Arvin Müller and Stefan Bötzel, in Bochum, but also with Pavel Volkov, who is still currently staying in Rutgers, and also Indranil Pool from Paris. All right, so let me start with something which I may be calling a bad news. So the bad news is that initially there was a lot of excitement on the experiment by Rio Shimano, and I also know that Stefan Kaiser was doing this kind of experiments where the idea, since you know that the amplitude fluctuation in a conventional superconductor known under the name of the Higgs mode do not couple to the electromagnetic wave in the linear response, there was a successful proposal that if you go to the nonlinear response, and for example, one of the way you can do a pump probe spectroscopy that is shown here, in typical conventional superconductor niobium nitride, or you apply multi-cycle pulse and cycle pulse and probe higher harmonic generation, you basically see response which is connected to the 2 times the superconducting gap, which you can very nicely see in the experiment by basically looking at the Fourier transform of your transmitted electromagnetic wave and the third harmonic generation, which looks like you're seeing a signature of the coupling between the electromagnetic wave and the amplitude mode, which is Higgs mode. Now, the problem comes if you start to do a real microscopic calculation, because the picture I've shown to you is on the level of the free energy, is actually that in a superconductor, the energy of the Higgs mode roughly coincides with the onset of quasi-particle continuum. And now if you do the microscopic calculation, and that was done by Lara Benfata and collaborators, it actually turns out that there is a term which is does not appear if you just write a free energy in terms of the coupling of the superconducting order parameter fluctuation with electromagnetic field, but there is a direct term which is proportional to the density of the quasi-particles coupled to the vector potential. It turns out that the Bogoliubov quasi-particle produce a very similar type of features in the third harmonic generation, except that 3 orders magnitude higher than the contribution you see from the Higgs mode, which essentially tells you that, and this is not surprising because even in the linear response, the coupling is weak. So even in the nonlinear response, the coupling to the Higgs fluctuation is still quite weak. So which basically tells you that the signatures, which is very likely you are seeing in the nonlinear response, in the pump probe generation, as well as in the third harmonic generation, is basically a response associated with Bogoliubov quasi-particle. And there has been still continuous discussion whether what you see can be still treated as a Higgs. In fact, if you are having a disordered superconductors, or if you have non-magnetic or magnetic impurities, you can effectively try to change the balance between what is called the charge density fluctuation. This is a contribution of Bogoliubov quasi-particle and the Higgs mode. However, essentially the bad news is that even if you are in a conventional superconductor is able probably to change the balance or to bring them to the similar order of magnitude, the problem comes in unconventional superconductors, because we know this most of the time should be in a clean limit, which basically tells you that everything that you see or everything what you should see in pump probe type of experiments is basically just a signature of Bogoliubov quasi-particles, which is also oscillating at 2 delta. But now I'm going to argue is whether you can actually use this third harmonic to see something more in pump probe type of experiments. Okay. And in this audience, I don't have to mention that the typical situation that you have an unconventional superconductor is that there is a overall repulsive Coulomb interaction, and this repulsive Coulomb interaction start to interfere with Fermi surface topology. And it's just a matter of, if you want, an accident that in the case of the cuprate superconductors, you have a nearly half-filled Hubbard band in the Fermi surface where you have a hotspot, and the superconducting gap due to repulsive interaction is trying to change sign, and you have experts in the audience, which is giving you a D-wave symmetry of the superconducting order parameter. But what you also know is that in principle, there is a whole zoo of the pairing instabilities nearby, and if you just slightly change your feeling, or change a little bit the details of the interaction, it actually turns out that you have a zoo of various instabilities. And even if the D wave is a dominant instability, the subdominant is always nearby and cannot be neglected as soon as you apply a perturbation, a nonlinear perturbation, which breaks inversion symmetry or diagonal symmetry of the lattice. So which basically is a starting point for me. So let's try to see whether in the third harmonic generation you excite immediately this type of mode, which have a name of the Bardashev-Schrieffer modes. And the most simplest example of it has been considered by Bardashev and Schrieffer, where you start with the effective pairing interaction, which is in the tetragonal system, can be decomposed into the S wave and D wave, and you take a situation that the S wave, which would be in this case an extended S wave, which is dominating, and you have an S wave ground state, but the D wave is nearby, and essentially you have a region where near the transition between S and D wave, where you expect a sizable D wave fluctuation in an S wave superconductor. Okay, so this is something that got quite an interest also in the linear response, especially in the context of the iron-based superconductors, where such a Bardashev-Schrieffer mode have been applied. So this is a summary of what is known so far. What you see in the linear response, it's in basically it's an excitation which is D wave in the S wave ground state. You cannot excite them at Q equal to 0, but as soon as you have a finite Q, you can generate it. And what is the most important, that it's visible in the B1G response. Now, so in a various iron-based superconductors, such a B1G type of the response in the S wave ground state has been observed. And also what is also interesting, that there is a number of this a mode that you see, and this is for obvious reason, because the symmetry of the vertex is chosen such that it's picking up a B1G type of excitation. You see that there is a subdominant mode which appears in the linear response. Now, the natural question, first question to ask, whether in the third harmonic generation or in a palm probe type of experiments, you can visualize this mode, and whether its intensity will be of the similar like Higgs mode, or maybe it will be the same order as the Bogolubov quadriparticle, which basically gives you a confidence that you are able to see. Okay, so the first way to look at it, in principle, you can start with description in Anderson pseudospins. You write your Hamiltonian, which is then looks like a standard Landau-Lifshitz type equation for the pseudospin basis. And important is that you can couple easily to the electromagnetic vector potential, because it couples to the pseudo Z component of the magnetic field. So this is sort of a known stuff, and in principle, it is known that if once you introduce a quench in an S-wave superconductor, you introduce, or via the electromagnetic field, you generate the Higgs oscillation and also the oscillation of the quasiparticles. But now let's move what's happening in the subdominant case. Necessarily, of course, you do excite a Bardashev-Schrieffer mode, because what is happening in this case that your pseudomagnetic field can be decomposed into the reducible representation. And basically, what you just need to excite a subleading dx square minus y square order parameter in the S-wave ground state is just to introduce an asymmetry in the vector potential, introduce the correct polarization of the light. So which is, you can immediately visualize. So in this case, if you would just look at the Higgs site of oscillation, you start to see that there is an additional mode, and this additional mode is basically your Bardashev-Schrieffer mode. Now, important thing is that first it is undamped, so its intensity is much higher than the Higgs mode, because the Higgs mode coincides with a continuum. And another thing that its form factor, it couples much stronger to the electromagnetic field. Now, in order to proceed further, you need also to treat phase fluctuation correctly. So you need to take into account that your phase fluctuation become plasmons. So you need to take into account the long-range Coulomb repulsion, which you also can do. The only price you have to pay is that you cannot do it in the Anderson pseudospin formalism. So you have to move to the path integral formulation, where you take into account also your long-range Coulomb interaction and basically do all the machinery by introducing all the collective modes in the dominant and subdominant channel and coupling to effective modes to the electromagnetic field. And now, if you do that, you can also compute the current and the third harmonic generation, which will be proportional to the third order of the vector potential and contains all the contribution coming from the collective fields. Now, so the first good news comes if you now look into the compare your third harmonic generation, for example, for particular parallel polarization of the field, you look at the third harmonic generation current. So usually what you have is that in experiment, you change it as a function of temperature, and what you're interested, you try to hit basically the position of the Bardassi-Schrieffer mode and at the same time the position of the Higgs mode. So once you don't have a Bardassi-Schrieffer, everything is dominated by what is an experiment called the Higgs, but I believe that it's mostly dominated by the BCS response. Important is what once you introduce non-zero interaction in the D-wave channel, you suddenly see that the response become dominant in the Bardassi-Schrieffer. And you only develop a kind of a shoulder, the charge density fluctuation, and the position of this Bardassi-Schrieffer mode is actually much higher than of the charge density fluctuation, which tells you that in a clean limit, if you're probing an unconventional superconductor and you see a response which is of the order of 2 delta, you better check that this response is basically coming not from what you believe is a Higgs fluctuation, but actually something which is more signature of the subdominant mode. And in order to do so, we also computed what would be the expected polarization dependence of this Bardassi-Schrieffer mode in the parallel and perpendicular component of the third harmonic generation current. And you can clearly identify the particular dependence, which is very different from the charge density fluctuations and also from the Higgs mode. Now, so you say, okay, so this you learn something about the Bardassi-Schrieffer mode, very nice, but there is of course a problem that you believe that you must be limited to the phase boundary between S and D wave superconducting. And my answer is, wait a minute, because actually we know that in the linear response experiment, when you probe what you believe is a Bardassi-Schrieffer mode in the superconducting channel, there is always some ambiguity, because if you go to temperatures which are well below the superconducting temperature, and this is one of this system, which is iron selenium, I'm going to speak also in a minute, where the superconducting transition temperature of the order of 10, 15 Kelvin, it actually turns out that the response in the B1G and B2G in the Raman already starts to increase well above the superconducting transition temperature, and actually is attributed as a signature of the nematic fluctuation, which actually orders around 90K, and this is also the reason why you have a drop of this intensity below the nematic transition. So then the question is, so you cannot consider in this system Bardassi-Schrieffer mode alone. You have to take into account that there is also nematic fluctuation. So which basically means that you have to come back and to reconsider your problem. And in this case, what you need to this is a phase diagram of this one of these nematic superconductors, where you see that that you can continuously tune the structure of also a nematic transition from being much larger than the superconducting state, but also towards the temperatures where they become closer and closer together. Okay, again, so what you basically need, you need to do the same calculation, but now you need to introduce also the nematic field. And again, the task is somewhat straightforward, because you need to include also, if you are considering in the, let's say, in a field, that would basically just effectively exchange your pseudomagnetic field by adding the nematic instability. And overall, you can also nicely cover this within this theory. Now, However, there is one question. If you are in the linear response, the signature of the nematic and Bardassi-Schrieffer still will be very different, because what you know is that nematicity naively would favor a state which is a S plus D state, where you break the trigonal symmetry and make it orthorhombic. Now, Bardassi-Schrieffer mode is a mode which is driving an S plus ID state, so where you additionally break a time reversal symmetry. Now, okay, so however, what is important is that now what you do is that you do all this machinery, and I don't have time to show you all the formulas. But what is important? Important is that once you are in the nonlinear regime, there is an additional dynamical coupling between the nematic fluctuation and your imaginary component of the d-wave order parameter, because if you are in the s-wave ground state, then you only have an imaginary component of your d-wave, the phase component of your d-wave order parameter. And what you actually see, so in the first case, if you start from analogous example, where you start from the s-wave ground state, but you assume that there are also two types of the other fluctuation, namely nematic fluctuation and fluctuation in the d-wave superconducting order, you see that they couple. We basically yield a hybrid Bardassi-Schrieffer nematic mode or composite Bardassi-Schrieffer nematic mode. And actually, it further boosts the position of this mode to the energies which are well below the initial Bardassi-Schrieffer mode that you expect. But what is more interesting is now to look into the situation when you are moving towards a state which is more correspondent to the pure iron selenium. And this is also very nice because this material can be grown as a large single crystal, and you can do all the nice measurements. But in this situation, you expect that the nematic transition is much higher than a superconducting transition in this case. Now, once you are in the mean field nematic order, there are two differences. So the first difference that you see is that we find is that once the nematic and order is of the order of superconducting and d-wave order parameter, let me remind you that because you break the diagonal symmetry, you have a S and d-wave order parameter which coexist. You still generate, in this case, a Bardassi-Schrieffer nematic mode by the virtue of the same hybrid coupling, dynamic coupling. But in this case, you can study the dynamics of this mode, and you see that it becomes a signature of approximate to the state, which was originally discussed by Jian Kang and Andrei Chubukov, that you can have a state where you have a relative phase difference between S and D wave component, simply because once you have a nematic order, the mixture of S and D is basically by the virtue of the biquadratic coupling to the nematic mode. But if there is an intrinsic instability, you will be able to see it as an additional mode. And you can probe its dynamics provided that you have. And it has a very peculiar dependence that I don't have time to discuss with. But what is more interesting is that this is a situation here that when you have a nematic order parameter which is completely dominating the superconducting state, so that means that you have a delta nematic which is larger than the expectation value, so the S wave and D wave component, and then you will basically see that the mode will become stiffer and essentially will acquire all the polarization dependence which comes from the nematicity. And this is where you basically can conclude that what you probe in the superconducting state is not just Bardassi-Schrieffer mode, but essentially a nematic mode with a corresponding polarization dependence. Okay, so why is that interesting? And that's first, let me tell you that something like this has been seen by the group of Yang Gallet, where they indeed found out that if you go to the, this is another example of the iron-based superconductor in the nematic state, where they clearly see the observation of another mode deeply inside the superconducting state, which, however, polarization dependence and angular dependence is not reflected of the pure Bardassi-Schrieffer mode, but basically more of the nematic mode. Now, why it would be interesting to look into the iron selenium? The reason is that in iron selenium, we don't know exactly the structure of the nematic order. So this is, however, what we know very well is how the electronic reconstruction takes place. And what is known is that if you start from pure iron selenium, there are 4 Fermi surface pockets, which with a corresponding orbital spectral weight. And once you go into the nematic state, the Fermi surface is also well characterized. Its orbital contribution are well known. It basically consists of the single orbital of the XZ character, a whole pocket near the gamma point, and an electron pocket, which is orthogonally oriented with respect to the whole pocket, and basically a mixture of the YZ and the XY pocket. Now, it turns out that in order to describe it, you actually, of course, you always break a B1G symmetry, but you actually need a combination of the nematic order parameters in order to correctly describe the resulting Fermi surface. So what you basically need, so by symmetry, you have a ferroorbital order, which is basically just splits the position of the XZ and the YZ orbitals. You have a D-wave bond nematic order, which is, let's say, S-wave form factor, but the cosine kx minus cosine ky, which is visualized here. Or you have also what you can dub as an extended S-wave in the momentum dependence, but the D-wave character is hidden by the phi3 in the combination of the orbitals. Or there is another one which is also allowed by symmetry, which is purely located on the XY orbital and dubbed as a phi4. And again, this is allowed by symmetry and was initially classified by Fernandez and Vafik. And actually, there has been an RG calculation which showed that you, at least according to the RG, you are having either these 3 order parameters dominant, and this one is very small, or the other way around, where the DXY nematicity essentially is dominating. Now, it actually turns out that the experimental situation is more complicated, because if you take a view that there is only these 3 order parameters, you basically try to fit what comes out for the resulting Fermi surface, it's unavoidable that you end up with a Fermi surfaces which contains an extra piece. This extra piece is this additional XY large Fermi surface electron pocket, which is located near the M point. And the problem is that experimentally, it hasn't been observed. So one of the way of explaining it is that you are basically trying to play with the orbital selective weights, that for some reason, this XY orbital is closer to the Mott transition compared to the other orbitals. And this is why you have a very small quasi-particle residue and you are not able to see it. Now, in the other scenarios that we proposed is that actually you need to have, so if you assume that the DXY nematicity is the largest player in the game, you can very nicely find out that you can get a quantitative agreement with a Fermi surface that is found to the experiment. And also something that I have not time to show, but you can see is that you can get very nicely all the superconducting gaps, asymmetries, and so on and so forth. Okay, so now my last slide is basically this one. So what is, so if you now want to distinguish between scenario A and scenario B, and so one of the important consequences of this scenario B is that you necessarily expect that as function of temperature or doping, in addition to the nematic condition, you have also a Lifshitz condition where this XY dominated electron pocket shifts away from the Fermi level. And there's this number of experiments that are in favor of this. And maybe one of the most recent is that if you look into the behavior of the susceptibility, uniform susceptibility below the nematic condition, you suddenly see a very non-monotonic piece, which is exactly coinciding with the onset of the Lifshitz condition. This is about the linear response, but what is also important that what you find in this regime where your Bardassia-Schrieffer mode is essentially nematic mode, which is just by the virtue of the coupling becomes a nematic mode, you can clearly see it change of the polarization across this transition, which can be used as a probe whether there is a non-local XY nematicity. Okay, Good. So let me stop at this point and move to the conclusion. So there are two main pieces in the conclusion. So the one is that in unconventional superconducting, if you see something in the third harmonic generation response, it is very likely not related to the Higgs mode. So it is either related to the signatures of the 2 delta coming from the Bogoliubov particles. But if you are lucky, the second mode, which appears at energies which are lower than the 2 delta, it is very likely a mode which is coming from the subdominant superconducting channel. And in the case, if there is additional particle Hall instability, and I believe the same can be said if you are having coexistence with, spin density wave state as well, that what will happen is that this property of this mode will be dominated by the particle Hall instability, like what I was discussing is the nematic instability. Okay, at this point, let me stop and thank you very much for your attention.